Hey guys, my name is Pedram and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Part 33, Bagging versus Random Forest. In the previous episode, we talked about the idea of tree-based ensemble method. We said that instead of working with one tree, why not take advantage of the wisdom of the crowd? Basically, we're going to combine multiple weak learners, multiple decision trees to come up with a strong learner, right? So now in this episode, we will be talking about what is Bootstrap aggregation, or for short bagging, and we are going to compare it with random forest. So the topics that we cover in this episode are going to be Bootstrap aggregation, random forest, hyperparameters, and feature importance. Okay, so bagging stands for Bootstrap aggregation. Imagine this is our original training set, right? We have 4 features. So let's say the number of features is 4, and we're going to show the number of features with with letter P. And let's say we have 5 observations. So n is 5, and our P is equal to 4. P is the number of features, right? Then we're going to bootstrap from this data. So what is the definition of bootstrap? Bootstrap means repeated sampling with replacement. So I'm drawing a sample from these 5 observations with replacement, and I do it thousands of times. So let's say the first bootstrap, so let's call it B1. This is the first bootstrap. Look at that. Observation number 1 shows up multiple times, number 3 multiple times, and number 4 once, right? So this is a subset of our the trained set, and the reason that we see multiple of these things is because Bootstrap in general is sampling from the data set with replacements, right? So I can have multiple observation number 1, multiple observation number 3, and etc. Right? And then look at that. The important thing is that all the 4 features, yeah, I keep writing M. So all the 4 features are used in this random draw from the model, right? So bootstrap number 1, then bootstrap number 2, bootstrap number 3, and etc. And then finally, this is our last bootstrap. Let's call it bootstrap number capital letter B, right? And look at that. In the bootstrap number 2, we have the observation number 2 has been repeated a couple of times, number 5 couple of times, and then 3 once, right? Again, this is another draw from the data set. And finally, the same story for the last bootstrap. So this step is called bootstrapping, drawing from the data with replacement. So random draw from the data with replacement. Now, we look at each bootstrap data, and then we build the weak learner on that, right? So we are, for example, we're going to use a decision tree and apply it to the bootstrap number 1 data, and then come up with a prediction, right? So this is the prediction, let's call it f hat of bootstrap number 1. We do the same, we use the weak learners, and we do the same for all the bootstraps. So f hat b2, and etc. And then finally, this is our f hat b capital letter B. So this part, these are ensemble trees, and then we are aggregating. At the end of the day, we will aggregate the outputs by, if it is regression, we look at the average of these. If it is classification, we look at the majority vote. So that's the idea of bootstrap aggregation or bagging. So bootstrap aggregation is a general purpose procedure for reducing the variance of a learning method, right? Again, I said it earlier, but remember, the way that Bootstrap is able to reduce the variance is that we know that the variance of sum of estimated variables is the variance. Well, let me actually write it down again, because this becomes very important when we want to talk about the difference between bagging and random forest. So we have, this is, let's say this is the variance of f hat, our ensemble method. It's going to be equal to the variance of f hat 1 plus variance of f hat 2 plus, of course, it depends on the covariance of f hat 1 and 2 and every other pairs, right? So if I have thousands of these Bootstrap, I will have thousands of these numbers. The entire thing divided by b. So this is a really important equation. So I want you to pay attention how the bagging and boosting are able and the random forest are able to reduce the variance. So we say that the variance of the ensemble method is going to be a summation of the variances, and we know that this the variances, the individual variances are going to decrease a lot. And also the covariance is going to be added, but the entire thing is going to be divided by b. So if we repeat this bootstrapping many more times, the variance is going to shrink even further. Okay. Now, we already covered this one. Given a training set, first we create b random samples. And then for each sample, a little small letter b, we build a decision tree. Again, this is our weak learner. We call it FB or F hat of B. It really doesn't matter. That's the estimated version. And after training, we have B decision trees. The predictions for a new data set observation X is obtained as average of B for regression or the majority of fault for classification. And this is a formula for that, right? So it's very straightforward. Whatever those prediction numbers were out of each decision tree, we're going to take the average by dividing it by capital letter B to come up with the ensemble prediction. And if it is classification, what was the most frequent prediction? Bagging is a very useful technique because it helps to improve the stability of predictions and protect against overfitting. So what does that mean? Remember, if you reduce the variance, if we reduce the model variance, we are reducing the overfitting. Right? Because again, if the variance is small, it means that if you try the model in the new data set or in the different versions of the data set, it's not going to overfit necessarily. All right, so that was the idea of bagging. Now let's see what's the difference between bagging and random forest. So random forest is a subset of bagging, right? It's a special case of bagging. And we're going to see that the random forest provides an improvement over the vanilla bagging algorithm. So the vanilla bagging algorithm is the one that we just covered, right? And it's going to do that, random forest improve the performance of the bagging by doing a small trick, and that trick is decorrelating the trees, right? So why do we care about the decorrelation of the trees? Going back to the previous slide, look at that. If somehow I can reduce the covariance between these trees, the variance is going to, the ensemble variance is going to shrink even further. So that's the advantage of random forest over bagging. So we're going to use a trick, and that trick is going to enable us to reduce these covariance terms. And it's a good thing if you can reduce the covariance term, because it's going to reduce our ensemble method variance more compared to bagging. Okay. Random forest uses a modified tree learning algorithm that at each split it inspects a random subset of the features. So it's not going to go over the entire feature set. It's going to look at the subset of those features, right? And this is going to do two things. First of all, it's going to increase the variation between the, when I say increase the variation, I mean increase the variation of different models that you're using, right? The model is a decision tree, but the data is different. We go over different features, and it's a good thing. And also is going to speed up the process, right? Because let's say we have thousands of features. So instead of working with thousands of features, each tree is going to work with a subset of those thousands. Let's say it's work with hundreds of them, not instead of thousands. Right? So in that sense, random forests are usually outperforming the bagging in general. The reason for doing this, by this I mean using a random subset of the features, is to avoid correlation of the trees, right? So we want to reduce the correlation of the trees. And think about it. This is a code from the Introduction to Statistical Learning in R. Our main textbook for the course, and it says that suppose there is one very strong feature in the data set. When using bag trees, most of the trees will use the same feature as the top split, right? And that results in an ensemble of similar trees that are highly correlated. So if I go back to the previous slide, look at this one. Do you agree that if we use all the features, okay, p is equal to 4, p is equal to 4, p is equal to 4, right? If you use, we used to have 4 features, and if I use all the 4 features, and these trees are going to be very highly correlated with each other, right? So in order to avoid that, random forest is going to do a trick, and the difference between random forest and bagging is here. It's going to work with a subset of features at each split, right? So instead of working with feature 1, 2, 3, 4, here it's going to only work with 1 and 4. In this tree, only 2 and 3. This tree, only 1 and 3, right? The features. So work with a subset of trees. And by this way, it's going to decorrelate these trees. And we know that if we decorrelate the trees, it's going to reduce the model variance even further compared to bagging, right? And yeah, the rest of it is the same as bagging. You know, we have Bootstrap, you know, random sampling from the dataset with replacement. And then we come up with different weak learners. And finally, we aggregate, right? However, be very careful. You know, in random forest, the random subset of features happen at each split. Right? So it's not like that we start with feature 1 and 4 and we use feature 1 and 4 for the entire decision tree, right? At the first split, we look at 1 and 4. At the second split, maybe we look at 1 and 3. At again, as we go over each split, well, this is a terminal one. So if we go over each split, a subset of features is going to be candidates, right? So this way, it is guaranteed that all the features from the model has a chance to show up in the algorithm, right? So even if at the first split you think that the model is missing one of the most important features, then you shouldn't be worried about it because those features have enough chance to show up in the algorithm down the road. Okay. Now let's talk about let's compare the performance of the random forest and bagging. So this subset of features, we're going to use letter M. So for example, M here is 2, right? Subset of features. Instead of 4 features, we're going to work with 2 features. Remember, our number of features was 4 in the original train set, and then M can be equal to 2 and can be any number less than 4, right? So now you can agree that if M is exactly equal to P, our random forest is going to be our simple bagging. So that's why I said that random forest is a subset of bagging, right? But in practice, usually we use the M to be very smaller than, than the P, right? So for example, we use P over 2, we use the square root of P. We use log to the base of 2 of P, right? And if I want to give you an example, imagine, let's say the original data has 10,000 features, right? So then random forest, instead of using 10,000 features, is going to, in this case, is going to only use 100 of them. You can see that how faster random forest can do the job, right? Because at each split, instead of going over 10,000 features, it's going to inspect only 100 features. So it's going to be a lot faster than decision trees for huge data sets, right? So this is another advantage of random forest against bagging. But here, let's look at the performance of the random forest versus bagging. Imagine we're talking about a classification model, and on the vertical axis we have test classification error. On the horizontal we have model complexity, right, or the number of trees. If M is equal to P, this is our bagging model. If M is equal to P or anything less than P, this is our random forest, right? So it seems that. So let's look at. So for example, around here. So it seems that at this point, at this complexity of the level of complexity, the bagging is out. Well, yeah, the random forest when M is equal to the square root of P is outperforming the random forest when M is equal to P over 2, and it's outperforming our bagging, right? Because remember, these are classification errors. The model with the smaller classification error is a better one, right? So as you can see, at some point, it seems that always the random forest model, let's call it random forest model number 1, is outperforming the bagging and bagging is outperforming the random forest model number 2, right? So again, depending on how we pick M, the random forest can outperform bagging or not, right? At least in this example. So this is going to be one of the hyperparameters that we need to tune when dealing with random forest models. So the most important hyperparameters for random forest are the following, right? So most of them are, there's an overlap between these hyperparameters and the decision trees, right? Because random forests are derived from decision trees. It's a tree-based model. But the new ones that we didn't see them in the decision trees are M and B. As you saw from previous slide, it makes a big deal how big change in the performance of the model how we use M, right? So the number of subset features, so this is one of the hyperparameters. Then the number of trees themselves, this is capital letter B. And in Python, it's called number of estimators. Remember, each of those decision trees is going to work as an estimator, right? As a weak learner. So we can say, okay, I want to work with 100 of those weak learners, or 500 of those weak learners, or 1,000 of those weak learners. Remember, the larger this number it is, the smaller the model variance. But there's some optimal level, right? By optimal, I mean that it's not worth to increase the computational cost by adding thousands of more trees if the variance model, overall variance model, is going to reduce only by a tiny little bit, right? Then the rest of them, we have seen these things before. The minimum size of each node or each terminal node, the maximum number of leaf nodes, the maximum number of terminal nodes. So how many terminal nodes we want to see, the maximum depth of the tree, and remember depth was the longest path from the root node to the terminal node. And finally, we can play around with the criteria itself. So if it is classification, we will use either Gini or entropy. If it is regression, there's no choice. We can always use RSS, right? Mean squared error or RSS. Then we can use grid search cross-validation. This, we have seen this before in our SVM algorithm. So we can use grid search cross-validation to tune the hyperparameters and pick up the best model. So the good thing about grid search is that we can get a better model by starting from some random values for the features. But the bad news is that it can be, we can end up in a local optimal, right? So because it's difficult to sometimes it's you do grid search cross validation and you'll see that your model is not outperforming as you expect compared to the vanilla version of the model with the default inputs. Okay, now let's talk about feature importance. So what is feature importance? So we know that random forest is relatively black box, and the reason that we say it's relatively black box because yes, we cannot interpret the model in general because basically we cannot track of all those thousands of Bootstrap trees down the road. But this doesn't mean that it's going to be entirely black box. So we can still rank the features. And this is a very powerful property of random forest in general. And decision trees, actually. It's not only for random forest. For simple decision tree, we can use feature importance as well. So let's look at an example. Imagine we are using the Logan housing data set. So this is a housing data set, and these are the features. So total square feet, garage capacity, total bathroom, total bedroom, year built, HOA, days on the market, sold terms, month sold, and etc. Right? At the end of the day, we can rank these features using random forest. What is it? So for example, in this case, in this example that we're looking at, in this example, it seems that total square feet is the most important feature among all the features. And then the next one is garage capacity and etc. And the least important feature in the model was irregular shape. So if a property has an irregular shape, it has the least important effect on the model, right? That makes pretty much sense. Now let's see how random forest is able to rank these features. Okay. So feature importance refers to a technique that assigns a score to input features based on how useful they are. So let's see what do we mean by score and how useful they are. So a score, if it is regression, the score is basically our RSS. If it is classification, we can look at Gini or entropy, right? Impurity index. Then by useful, so for regression, we look at each feature and we see each feature is reducing, for example, in regression, is reducing the RSS by how much, or each feature is reducing the Gini and entropy by how much, right? So this is what we mean by useful. So for random forest, the total amount that the RSS is decreased or the Gini index or entropy is decreased due to a split over a given predictor, average overall B3s. So this is basically that score that we're talking to. A large number indicates important predictor because a large number means a larger reduction in the RSS, a larger reduction in the impurity, right? And so if you want to think of an example, so imagine we have thousands of trees, and this total square feet is going to show up thousands of times among those for each split among those trees. And then at each split, we're going to record, for example, how much this Gini or RSS reduced. And then we're going to add up all those numbers for the entire model and then report that number, right? So this number, for example, it's 0.35. And this number is going to change based on the units of the variables, of the target variable, and if it is classification versus regression. So basically, we cannot interpret this number in terms of magnitude. So but we can simply rank the features, right? So we can say that, okay, total square feet is more important than the zip code, than the years sold, and etc. But we cannot say anything about this quantity itself. It's not interpretable.
Okay, so that's pretty much it. In the next episode, we are going to talk about the advantages and disadvantages of the random forest. Until then, take care.